We have a few steps to arrive at the governing master equation of passive Mollacking. The last effect is the constant phase shift. The last two effects are about phase modulation. For example, the cell phase modulation effect. Here we assume the maximum phase shift due to Kerr effect is still much less than pi. In this case, the new pulse is the old pulse multiplied with pure phase modulation term, e to the minus j delta coefficient, which is the SPM coefficient, times the envelope power of the driving pulse. And due to the assumption that even the maxima Kerr phase shift is still much smaller than pi, we can use first order Taylor series expansion. So we have this new relation. The phase modulation term is replaced by 1 minus j delta times p of t. So you can combine with the previous step and only preserving the lowest order terms. You can arrive at this equation. Then finally, we have to deal with the CEP shift, carrier envelope phase shift. The physical origin is quite simple. We know the phase velocity of carrier differs from the group velocity of envelope. Okay, you must have known the formulas. They are different. Group velocity is about derivative, and the phase velocity is about the slope. Okay, 一个是切线，一个是割线斜率。So they are essentially different. If they are different, that means when pulse travels within the cavity, after one round trip, the relative position between the envelope and the fringes can be drifted by a certain amount. Okay. This is so-called the CEP phase shift. But here, we also assume the CEP phase shift per psi is much smaller than pi. So you can write down this relation. Okay? The new pulse is equal to the old pulse times a CEP phase shift e to the j per psi. And if per psi is very small, it's close to 1 plus j per psi, then you can borrow the equation derived in the previous slide, okay, inserted here. And here you can cancel 1 and 1 together. Then you arrive at the final complex master equation of general passive Mollacking. Okay. So this is the complete governing equation for passive Mollacking. It's basically it's a second order ordinary differential equation. You can see second order time derivative here. So it's a second order ODE. Okay. So as long as the effect of each element is quite weak, remember, we have assumed cell phase modulation, dynamic loss, gain, and the CEP is relatively weak per round trip. Then this equation should work. Okay? And for general passive Mollacking, that means it contains amplitude modulation as well as phase modulation as well as the CEP phase drift. Everything has been taken into account. Okay, so that's it. But I have one very small question. Could you identify the meaning of each term? Okay. So for example, without remembering anything, could you tell that this term, j times d, with a second order time derivative is associated with dispersion? Of course, we know symbol d means GDD parameter, right? So if you remember it, you can interpret, okay, this is about dispersion. But without remembering the symbol, could you identify that this term means dispersion? If you can, then this equation makes sense for you. Otherwise, it's simple. It is simply something you have to remember. Just for the time being, it does not help much, right? So, could you interpret why this term means dispersion? Can you justify it? One trick is, do you know the meaning of second order time derivative in the frequency domain? It means omega square, right? And omega square with a purely imaginary part, it means phase, right? If you are real part, it's about amplification or loss. But if you are talking about purely imaginary part, it means phase term. A phase term with proportional to omega square. So it means a parabolic phase, right? A parabolic phase certainly is associated with dispersion, right? The lowest order dispersion. Of course, we did not consider higher order dispersion like cubic phase. It's not included in this model. But quadratic phase modulation is taken into account here. Okay? So for the same reason, could you identify the physical meaning of this term? 1 over omega c squared with second order time derivative. The strategy is the same. This term is minus omega squared in the frequency domain. But this is a real part term, right? So it's not about phase modulation, it's about amplitude modulation. And it's proportional to omega squared. So it means a parabolic modulation in the frequency domain. What's that? Something like this. In the frequency domain, it's about transmission, right? So this is a filtering effect. So if you review the derivation process, you can identify this is about the filtering effect of the gain medium. Okay. Then you can apply the same strategy to each term. If you can do that, you can interpret the physical meaning of each term. Then this equation makes sense for you. Okay. Good. So let's move on to the next section, passive mode locking with self-amplitude modulation only. Okay. So the idea is we intend to simplify the master equation we just derived. So starting with the assumption that only amplitude modulation is taken into account, no phase modulation at all. Okay? And under this condition, we can arrive at some easier conclusion about the general characteristics of passive mode locking. Okay. But before we are working with mathematics, let's ask ourselves this question. Does fast satural absorber really exist? Okay, remember the model here the model we are going to use is about fast sexual absorber. Do you still remember the meaning of fast sexual absorber? Your absorber has a response time, say tau sub A. If tau A is much shorter than which quantity? Your driving pulse width. Then this sexual absorber is regarded as fast sexual absorber. Okay? But does fast sexual absorber really exist? Okay, this is an interesting question. The recovery time, tau A, of common sexual absorbers are like this. For example, semiconductor sexual absorber, which is quite popular, tau A is in this range, tens to hundreds of picosecond. Okay, 10 with S means 20s, 30s, 80s, tens of picosecond to hundreds of picosecond. Already very fast. Okay. And decades before, people usually used the dye lasers. Dye is a very popular medium as gain medium and as sexual absorber. The response time is about tens of picosecond, really fast. Okay, that's one of the reasons dyes played a pivotal role in early Morlock lasers. Okay, but not anymore. You can hardly see any dye lasers now. If you are talking about a very new material, graphene, the response time is even faster, say less than 1 picosecond. Okay, so it could be the fastest sexual absorber you can access to date. But even though there is no real fast sexual absorber for femtosecond pulses, if your laser can generate like 10 femtosecond pulse, all of these are relatively slow compared with your pulse, right? So under our definition, they are all slow sexual absorbers. They are not fast. Okay. Then even the fastest material, graphene, is still slow compared with the pulse you intend to generate. So in theory, this model is useless, right? Then why should we pay attention to this model? If you can never find a real sexual absorber which is fast enough to fit into this model, why should we pay attention to this model?
Maybe in the future we will find one.
Yeah, you are far sight, right? I know that. But this model has been used for many, many years. So it's not about future. It's about now and then. Okay. So the answer is like this. Although in real world, you can never find a material fast enough, at least to this state. Okay? But you can produce artificial fast sexual absorber by nonlinear optical effect and the design of laser cavity, which will be the central topic in the last section of this lesson. Okay? 所以实际的材料没有办法给你真的所谓的快速的饱和吸收体，但是你可以制造出等效的快速饱和吸收体，not depending on material, but interplay between nonlinear optical effect and the design of laser cavity. Okay, and we know nonlinear optical effects such as Kerr effect is supposed instantaneous effect, right? As I mentioned, Kerr effect could be in the order of 1 femtosecond, truly fast. So usually it's treated as instantaneous effect. And this effect is faster than the pulse you want to generate. And the interplay with cavity, if there is nothing about material response, the total effect could be equivalent to a fast set of absorber. Okay, and it has been done many years before, so that's why this model is very useful. Okay. But we will see a real example in the disulfide laser analysis. Then you will understand what does this mean. Okay, so here I summarize the assumptions we made for section 4-2. Okay, we assume the absorber is fast, so tau A is much smaller than delta T. Delta T means the pulse width. Tau A means the recovering time of the absorber. Okay, we also assume weak loss saturation. In other words, the peak power of the pulse is only moderate. Okay, so peak power is much smaller than the saturation power of the absorber. Okay, P peak much less than PA. So be careful if in the end your pulse has a very strong peak power, this assumption is violated. Maybe this model is no longer accurate. You have to slightly modify your model further. Okay. We also assume the gain is slow. This is usually true. The gain recovering time, tau g, is much longer than TR. TR means repetition period, pulse-to-pulse spacing. Okay? Not to mention the single pulse duration, delta t. Okay, so for example, in a disulfide laser oscillator, TR is usually in the order of 10 nanoseconds, but delta T is in the order of like 30 femtoseconds. So this is true. And for a disulfide gain medium, tau G is in the order of 1 microsecond. So 1 microsecond, much longer than 10 nanoseconds, much longer than 30 femtoseconds. So this assumption is usually true. We also assume the gain saturation is also weak. So your pulse energy can only be moderate, or U total is much smaller than UG. UG is the saturation energy of the gain medium. Okay. Do you still remember the definition of UG? Okay. When your pulse energy equals UG, what does happen? Your gain, when the pulse drives the gain medium, the gain will drop, right? And the gain saturation is obvious if your pulse energy equals to or larger than UG. But if this is the case, total pulse energy is much less than UG, then the saturation is nominal. You can hardly identify the saturation. So you can imagine the dynamic gain curve is almost flat. It's insensitive to the driving pulse. 如果这个条件成立，你可以想象那个 gain 随着脉冲的通过，它改变是很小的，看不太出来。gain curve 几乎是一个水平线。This is our assumption. The last three assumptions are about phase modulation, right? We assume no GVD, so D coefficient is 0. We assume no cell phase modulation, so delta coefficient is 0. We assume there is no CEP shift, so constant phase psi is also 0. Okay, so the last three terms are about phase modulation. They are all 0 under our assumption. Okay. Any questions? So mathematically, if many terms are 0, it should be happy, right? So let's check what happens. Starting with the fast set of absorbers. If you still remember, this is the conclusion we had in lesson 3. The red one is the driving pulse. The green one is the dynamic loss curve. If the absorber is fast, then loss curve can respond to the driving pulse almost immediately. Okay? And the model we used before is like this. Loss as a function of time equals L0 means small signal loss. The loss when there is no laser power. The loss is highest, which is L0, over 1 plus a positive number, which is P of t over PA. P of t is the driving pulse, the red curve. PA is the saturation power of this absorber. Okay? And the L0 formula is here. If you see N sub A, it means all the electrons are on the ground state. So the loss is highest, small signal loss. Saturation power's formula is here. A sub A is the beam cross-sectional area in the absorber. Sigma A is the equivalent cross-sectional area of the material, which is a very small number. It describes the intersection area when photon and the atom can effectively interact with each other. Okay? U0 is the single photon energy. Tau A is the response time of the absorber. Okay, so everything we had before. But under our assumption here, in the previous slide, peak power, even the peak power, is much smaller than saturation power. Then you can use Taylor series approximation. L of t is no longer this one, but L0 times 1 minus P of t minus over PA, or equivalently, L0 minus a gamma coefficient times your driving laser power, P of t. Okay? And in this model, the gamma coefficient is L0 over PA. You just compare the coefficients. Okay? And this is the so-called self-amplitude modulation coefficient, or SAM coefficient. Okay. Could you tell why it is referred to self-amplitude modulation? Okay, if you check the formula, your loss as a function of time equals a constant minus a proportional coefficient times the driving laser power. So the logic is very similar to self-phase modulation. This is amplitude or loss modulation. And it totally reflects the shape of the driving pulse, right? If you have a triangular pulse, P of t is a triangular function, then L of t response is a triangular function. If this is a square function, you got a square loss curve. So the loss totally depends on, depending on the driving power. So that's why it's referred to self-amplitude modulation. Okay? And the other thing is what happens if you have a bigger gamma coefficient. What is the meaning of gamma coefficient? This is a proportional constant, right? The bigger the gamma, that means your loss curve is more sensitive to your driving laser power, right? Even a moderate driving laser power can deliver very strong impact on loss curve, L of t. If gamma is very small, then the loss is insensitive. It's less sensitive to the driving laser power. Okay. So what do you prefer? a stronger or a weaker self-amplitude modulation coefficient in terms of pulse generation? Yeah, intuitively, you prefer a stronger SAM coefficient. If it is 0, there is no pulse shortening effect. If it is bigger, we expect the shortening effect is stronger. However, things are more complicated than your imagination. We will discuss this issue later. A very strong gamma can be good, but can be worse sometimes. Okay, we will see that later. Okay, so here I show you if the saturation power, if the peak power is about 20% of the saturation power. So it's roughly satisfied with this assumption. What is the difference between the original formula and the approximated formula? Is there any big difference? Okay, so this is the result. If you use the approximated formula, you got the blue dashed curve. If you use the original formula, you got the green curve. So basically, okay, they agree well with each other to some extent. But if your peak power is stronger and stronger, the difference could be larger and larger, and eventually this model is no longer accurate. Okay.